Chapter 14, surprisingly still. No. Yes. All right. So we got into titrations last time. We finished up our conversation there about buffers, and we kind of finished up most of the lab here today about buffers. But a reminder, as we've been talking about, again, our Henderson-Hausbach equation is the one that we want to use in any type of buffer situation, which really is, again, a common ion surge situation. As we've talked about a number of sort of examples that we've done and talked about, you can obviously use the Henderson-Hausbach equation. You can still, as we saw, use an ice table if you want to solve these problems. Once again, if it is a buffer, you got to have that initial on both sides for it to properly work. We also talked about, which is also important for titrations that we got into, the idea that whenever we add volume, the molarity consistently changes. So when we do an ice table that involves volume, we do need to do it in moles. And after that first ice table, you do want to convert back to molarity at the end, and that's typically the total volume. So in the case of a buffer, kind of like what you did today, you had so much of your buffer, right, 20 mils, and you added maybe 5 mils of like the base or acid to it. So again, adding those total volumes, converting it to liters and converting it back to molarity. It's really good practice. Again, as I mentioned, technically speaking, if you left them in moles and went into the Henderson-Hausbach on a buffer problem, you will get the same answer as if you converted them back to molarity and went into the Henderson-Hausbach equation, because the volumes will cancel each other out when you're doing that division part right there in the equation. But there will be calculations, especially in titrations, where you will need the molarity. So like I said, just get it back to molarity, and you'll always sort of have it in the right sort of unit that you need to finish the problem. That led us to our wonderful journey of titrations and the age-old question of why I added that one drop and it turned pink. Now you know the answer, hopefully. And again, the answer is because it goes pretty vertical, right? As we go towards the equivalence point there. And as we talked about, what that means is as we get near the equivalence point, we typically will see a jump in the pH to the equivalence point, and then we'll see a jump after the equivalence point in pH. And that's really affects the colors that you see in like an indicator like phenolphthalein. I won't attempt to spell it again, but it starts with a P, 8.3 to a 10. And as we talked about, it is colorless really in acidic and neutral solutions, starts to turn pink in basic solutions around 8.3-ish or so, and gets darker pink as you go that way. So as we talked about, if you missed the equivalence point by a drop or two, you could find yourself here on the titration curve, which in terms of the volume of the equivalence point is probably pretty close to where you need to be anyways. But that's why you see that really sort of dark color. The reason, again, we talked about why maybe some instructors might have you re-titrated at that point is because you could also get kind of the same color way over here, far away from your equivalence point volume. And again, that would not be good in your calculations. So when we do choose an indicator, as we talked about, it's really important to choose one that you can see a visual change in the color of the solution near the equivalence point. So that's what you're looking for. We'll see some lists towards the end here of some different types of indicators. Some change colors in basic solution like phenolphthalein, others change color in more acidic solutions, which would be good for a different type of titration where your equivalence point might be acidic. But you definitely want something where you can actually see the color change. You don't want to pick one where by the time it gets to the equivalence point, the color is already changed, because you still won't know where to stop the titration. And that's sort of the purpose of the indicator, right? Is give you a visual representation that, hey, you should probably lay up your titration at that point. The important part of a titration curve, as we talked about, is most of them will kind of look like this S type of shape with our equivalence point happening here, a little pH and some volume of, say, sodium hydroxide or base maybe being added. And there's really kind of 4 parts to pretty much all titration curves. There's really the part over here where we first start the titration, or before we start the titration, really. The second part is when we start the titration to before the equivalence point. The third part is at the equivalence point. And in an acid-base titration, the important thing to keep in mind is the moles of the acid at that point will equal the moles of the base. So that is exactly where the equivalence point should be. If you're adding base to your acid, that's the point where you've added exactly enough moles of your base to use up all the acid that you started with. The good thing about titrations we will do is we will continue through and get the rest of the curve there, which is really the fourth part of the titration curve, which is what happens after you go sort of past the equivalence point. We're going to talk totally about 3 different types of titrations that can happen. And we were in the middle here of the first type. So let's just pick it up there and talk about what we were looking at here. So this is a titration of a strong acid with a strong base. And once again, here we'll get a little equation action happening here. All right. So as we talked about in this type of titration, we are in this case adding the sodium oxide from the burette to our acid in this case, our HCl. So that's why we do see an acidic pH here at the very beginning part of the titration. And as we talked about, pretty much before you add any sodium hydroxide at that very first step, you pretty much only have, in this example, hydrochloric acid, which is a strong acid. And once again, because it's a strong acid, that's pretty much going to give you your H plus concentration because it will completely break apart into ions. And that means in this type of titration, if you want kind of your opening pH, you can actually go directly into the pH equation using the concentration of the strong acid, which will essentially give you your concentration of your H plus. Now we got to the second part as well. And in the second part, when we start adding sodium hydroxide in this example, which again is going to take us to the equivalence point, basically, we will get a reaction that will happen. And it is that one that I wrote above there. We'll get our HCl and our sodium hydroxide reacting with one another, making our sodium chloride and our H2O. So as we talked about here, this will require an ice table to be done at this point in the titration. We do want to do this ice table in moles, right? And what we talked about was, because we are adding, in this case, the sodium hydroxide to the strong acid, the moles of sodium hydroxide in this case should be less than what we started with. So I think I made up 4 and 2 was my example I think I used. And at this point, the sodium hydroxide that we're adding, because we are before the equivalence point, and every time you are before the equivalence point in any type of titration that you do, the moles of whatever you are adding is always going to be less than the moles of what you started with, like in the beaker or the flask or whatever you might be titrating with. So that means that the sodium hydroxide in this part would be our limiting reagent, and our excess reagent really would be the HCl. So the change, as we saw, was the 2 moles that came from the sodium hydroxide in our example. And at the end, we would have 2 moles of that. We'd have nothing of that. All the sodium hydroxide should be gone. We would have 2 moles of this. Once you get to the end of your ice table, once again, we want to convert back to molarity, as we talked about, using the total volume. And at this point, you can always look at your ice table to see what you have left over. And at this point, we do have sodium chloride and we do have HCl. And as we talked about the other day, again, that is not a buffer. So remember, just because you got 2 numbers, it's not a buffer. Even though they are related to each other, the problem with this not being a buffer is, as you mentioned before, it is a strong acid, right? And I feel like I'm on the wrong titration picture there, but that's okay. I guess we'll come back to this guy in a second. So this is the wrong titration picture, but it's okay. So because it's a strong acid at this point, you would just take the concentration of the H plus, which would be our strong acid, and then go into the pH equation at that point. So anywhere that you start the titration with the very first drop there, until you get to the equivalence point, you do need to do, in this type of titration, 1 ice table done in moles. The purpose of the ice table is to figure out how much of your strong acid you still have left over. You then need to convert it back to molarity and go into the pH equation, basically, to calculate the pH at that point. I think we finished up coming back this way at the equivalence point of what happens here. And at the equivalence point, which is the third part, we definitely have our reaction still occurring. And because we are at the equivalence point, we should have pretty much equal moles of these guys, because that's basically the definition of equivalence point, which once again means you can't really choose the wrong number, as it should only be the only number present at that point. And that's going to basically zero out everybody here, which is what we would expect to happen at the equivalence point, because we have equal amounts. That will leave us 4 moles of this guy, which we then convert back to molarity. Once again, we will have this salt that is left over at this point, which is a neutral salt, and really at the pH, not the pH, at the equivalence point of a titration of a strong acid and strong base, you should expect a pH of 7. And again, that's why it's sometimes called an acid-base neutralization reaction. They basically neutralize themselves, and you still should not drink it. That was your next question again. All right. See, I have good memory. I remember the question. All right. So I think that's where we left off. Any questions up to that point in this type of titration here? All right, let's finish out this type of titration when we find the right curve, wherever that curve went. Back this way, maybe. Let's go back that way. There it is. That looks more like it. All right. All right, so at this point here, we're going to be looking at really the fourth part of this titration curve, which is basically after the equivalence point. So at this point, we are going to be definitely after the equivalence point. So we will still have the reaction. It's going to be the same one in this example. We'll do a little bit of that. And we will do a little bit of that. So sodium chloride. Once again, here we are actually past the equivalence point. And we are still adding this guy, and we are still starting with this guy, right? So in this case, we will do this in moles, once again, using my same sort of starting moles I made up last time, which is 4 moles. But in this case, because I am past the equivalence point, the moles of sodium hydroxide should be less than, equal to, or greater than 4. In this example, should be greater than 4, right? Because we're definitely past the equivalence point. So I'm going to go with 6. Feels like a good made up number again. At this point, what happens is you're basically ignored that really dark pink color you probably have at this point, and you're just adding sodium hydroxide and dropping it in. So in this case, we're actually going to have our HCl become like the limiting reagent in this case. And we definitely, because that indicator didn't stop you, you kept going, you have plenty of sodium hydroxide that you're dumping in there. You still maybe have a half a beerette full. Why not? Let it go, see what happens. So the thing that's going to affect is obviously the change part here. Because the HCl in this case will now be our limiting reagent, it is actually going to be the one that's going to be the change is going to occur here. And again, as we talked about, logic tells us we can't take the bigger number because it will give us a negative number, right? So that's always something to keep in mind. That's going to give us 0 here. We'll have a couple of moles here, maybe 4 moles here. Just like normal at this point, I would recommend converting yourself back into molarity by dividing by the total volume. Once again, we could use our ice table to try to figure out maybe what is going on. First off, we have these 2 things left over, which is sodium hydroxide and sodium chloride. Is that a buffer? It is not a buffer. So we have 2 things here. We have a salt, which we've seen a lot up to this point, and this salt is still a neutral salt, which means we don't really need to worry about that. That pretty much means we have just this one thing left over, which is sodium hydroxide. Sodium hydroxide is a base, and what type of base? It is a strong base. And because it's a strong base, that means it's going to pretty much 100% break apart. And that means you essentially have not the H+ concentration, but you have the OH- concentration, right? So that will allow you to go into the POH, probably would be a good move. And once you go into the POH, you then could use the pH, right, is 14 minus the POH to get to your pH value, which is probably what you're looking to calculate. So when we go past the equivalence point in this type of titration, we're basically just dropping in a bunch of sodium hydroxide. And if we kind of look at what's happening in the beaker at that point, as it drops in, you're basically just adding a bunch of hydroxide from that sodium hydroxide. And that is why we do see a big spike in the pH, right? After the equivalence point. And that's because at the equivalence point here, they're equal, right? Which means you don't have any excess hydroxide. But as soon as you add more hydroxide past the equivalence point, you just flooded it with hydroxide. And that's why we see this really big jump in pH past the equivalence point, because you added a bunch of hydroxide really quickly to it. And that's also why we get that big jump, obviously, in the color of our indicator and also the pH as you continue to do that. Any questions on that? All right, so 4 different spots on this titration curve. And again, we're specifically talking about this type of titration where you're taking a strong acid and a strong base together. That is how you calculate the pH anywhere along the way. So now you will calculate the pH somewhere along the way. And why don't we do, let's say we did this titration and we want to know what is the pH after we add, we'll do 27.5, why not, milliliters of 0.1 molar sodium hydroxide to, let's go with our friend, 25 milliliters. Look at that, an extra 0 there. I'll just leave it like that there. Milliliters of 0.1 molar hydrochloric acid. All right, give it a go, calculate pH, see what you come up with. I'll do it as well. Made up some numbers. All right, let's take a look. As I feel like I hear a piano somewhere. Maybe it's just me. I don't know. All right, so we are taking a look at this one here, and it's a titration. Once again, we are adding our sodium hydroxide here to our HCl. So we're definitely going to get a reaction, and that's going to be our HCl and our sodium hydroxide here, and our sodium chloride, and a little H2O. Obviously, we are adding volume here, so we need to get everybody into moles. So for our sodium hydroxide here, we need to convert our volume into liters, divide it by 1,000, or move the decimal place 3 places to the left there. And we're going to times it by the molarity of 0.1 moles per liter. That's going to get us a 0.00275 moles of sodium hydroxide. We're going to do the same thing here for our HCl. We have 0.025 liters times by its molarity of 0.1 moles per liter. And that's going to get us 0.00250 moles of HCl. Any questions up there? All right, so let us go into our table here, see what happens. So initially here, we got a 0.0025 moles. We have a 0.00275 moles of this guy, nothing going on there. Again, we are starting with this guy here, which is our HCl. We are adding this guy to it. So now you're going to tell me, am I before, at, or after the equivalence point? I am after. And we can use our ICE table to know that by looking at the numbers we have. So if you're not sure from the question that you are past the equivalence point, don't overlook your ICE table. It could help you. We know that at the equivalence point, right, the moles of the acid and base should be the same number. And since we are starting with this guy, and we look at this guy, we can see that we have more moles of what we added than what we started with, which means we could only be after the equivalence point. Obviously, if we did this and we had less moles than we started with, then we would be before the equivalence point. And obviously, if we had the same number of moles, we would be at the equivalence point. Any questions on that? That's really important because we are past the equivalence point, that means really here our acid is going to end up being the limiting reagent here and get used up, as it is the smaller number, and we can't obviously use the larger number. So that is what we're going to subtract here. And that means that when we reach equilibrium, we got none of the HCl left over. We got 0.00025, I hope, moles. And over here, 0.00250 moles of this guy. At this point, we do want to convert back into molarity here, and our total volume at this point in our titration is we started with 25 milliliters of our acid. We added 27.5 milliliters of our base there in this case, and that's going to get us a net of 52.5 milliliters as our total volume, which we want to convert to liters and divide everybody by. Divided by 1,000 or move the decimal place. And if you want to do both of them here, you can, I guess. And if we do that, 0.00025 divided by 0.0525, gonna give us 0.004762 molar, and 0.00250 divided by 0.0525. Going to get us 0.047619-ish molar in that case. First off, any questions on the calculations so far? Once again, if you are not sure what you should do at this point to get to the pH, this is why writing the equation correctly, doing the ice table is really important. You can look and see what you got going on. And as we talked about previously, we basically have that sodium chloride, which is a salt that's not going to do much, which means you don't have to worry about this number. We have, as we would expect at this point in the titration, excess amount of sodium hydroxide, which is our strong base. And because that is sodium hydroxide, that means that that number right there is our OH minus concentration. So at that point, we could go into our POH, which is going to be minus the log of 0.004762. Minus the log of, not that number, try that number there. It's going to give us like a 2.32. So again, at this point, if you, for some reason, thought this was the pH, it should not make sense, right? Because that would be like an acidic pH, and you're dumping a bunch of base in there. So that should not make sense to you. So you want to think about these things as you're doing the calculation. That means we do want to use our pH plus the POH there is going to give us our 14. And that means that our pH in this case will get us a 14 minus 2.32. And that means we are like an 1168, which is definitely basic and would make a little bit more sense, yes, than the 2-point-something number for the pH. Any questions on any part of that calculation there? We can, in this example, see how we did. We were 27.5, which is like in this area. So we're kind of between those numbers. That's pretty good. Not bad. Worked out all right. Any questions on strong acid, strong base titrations? You need to be able to recognize the curve, know the different parts of it, and frankly, be able to calculate any pH I choose, including like 300 points along the curve. Yes. In case I'm really upset with you at that point. Here's just a simple test. It's just one titration curve. Give me the pH at 400 points along the way. All right, then let's talk about the next type of titration, which is a little bit different. Question? For this? In this situation, you can't do the Henderson-Hausbach because you don't have a buffer. So you need a buffer to do that, which will be coming up shortly. Yeah, but definitely in this type of titration, you probably shouldn't be using the Henderson-Hausbach anywhere near it. Just leave it on the side, walk away slowly. All right, all right. Now let's talk where maybe you can walk back to it later here on the next type of titration, which is the next type of titration we're going to talk about after I clean up my graffiti here with the page. Get rid of what I wrote earlier. Is this type of titration, which is a weak acid and strong base titration. So again, the difference here between the one we just finished talking about and this titration is the acid. So we actually have a weak acid in this case rather than a strong acid. The orientation of sort of what's going on is the same. We have our base up in the burette and we are adding it to the acid. And so if we look at a titration, for example, of everybody's favorite example, which is acetic acid, plus some sodium hydroxide here. And again, that's acetic acid, also sometimes written C2H4O2 as well. This is going to be a double displacement reaction happening here, going to give us a little sodium acetate action, I think. And maybe a little H2O as well would be good. Yeah. So again, basically the H and the OH, sodium and the acetate going to come together in that case. All right, so you can take a look at our titration curve there, which is very similar to the previous one we saw. It still has that sort of traditional S sort of shape to it. And we still have the same 4 points on this titration curve that we did on the other. So we have before we start the titration, we have once we start the titration to before the equivalence point, we have the third part, which is the equivalence point, and then the fourth part of the titration there going to be after the equivalence point. So we're going to talk about, like we did on the previous one, what happens at each of these parts. So let's start with the first part, which is before we start the titration here. So before we add sodium hydroxide. So before we add sodium hydroxide, the only thing I have sitting in my beaker, right, is in this example, my acetic acid. And if I want the pH of acetic acid, which is a weak acid with a Ka value of 1.8 times 10 to the minus 5, how would I find the pH of a weak acid? I need to do what? I put it in my drink to cool it down. They float to the top. I could get it crushed R cubed. Ice, yeah, so we should do an ice table here. That'd be good. Wow, okay, I'm not gonna cut that out. I'm just gonna leave that in the video. That's what I'm saying that. Yes, we go to the thirst oasis, crushed ice, of course, right? Yes, cubed ice. No one wants cubed ice. But we would do an ice table here as it is a equilibrium problem, right? Just like we did in the, I would say, previous chapter, but we're still on chapter 14. At the very beginning of this very long chapter, when we did Ka type of problem, right? So because this is a weak acid, it is different than the last one where we have a strong acid that's going to completely break apart, right, into ions. Because it's a weak acid, we would have to do a Ka problem here. So a little bit different than the last titration. We will have to set up an ice table where we just have the weak acid dissociating in this case. And we would do this one in molarity because we haven't added any volume of sodium hydroxide. So we could just use the initial concentration of the weak acid. And the rest of the table would be just like all the tables we've done up to this point. We would use some X's. So in a lot of cases, if you're doing an ice table with moles, you're going to use numbers instead of X's. And if you use molarity, a lot of cases, you'll use X's. So here we do our initial concentration minus X. We would have X and X. This obviously would go into our Ka expression where we can solve for X. And again, you can make your assumption like normal, quadratic it. What we do see again at the point when we do solve for X, X will equal the H plus concentration, which means at that point you then could go into your pH equation. So this one obviously is a little bit more entailed because it's a weak acid versus a strong acid. But the good news is you've done this calculation before, I hope, yes, and you remember it. So it's just a regular Ka one where you have to do your ice table, get your X value into the pH equation. It will be a weak acid. So in comparison to maybe the strong acid titration, we may see the pH starting a little bit higher in terms of where the previous one did, but it's still going to be acidic at this point. Any questions on before you start the titration here? All right, so now that we feel good about starting our titration, we're going to carefully add 1 drop at a time. And that's going to move us into the second stage here of our titration curve. We do see that because we're adding some sodium hydroxide, we do start to see the pH start to rise as we're doing that, which does make sense. Again, here we're still starting obviously at an acidic pH because it's a weak acid. So let's talk about what happens here at part number 2, where we have added some sodium hydroxide. but we are definitely before the equivalence point. Yeah. So when we start adding sodium hydroxide to our acetic acid, we will get that reaction that we saw earlier, which again is our acetic acid plus our sodium hydroxide going to do a double displacement reaction and make some sodium acetate and a little bit of water. Now, because I'm adding some sodium hydroxide at this point, I do need to do a ice table, and it should be done in molarity or moles. It should be done in moles at this point. So once again, here I'm going to make up my starting amount, and I liked 4 last time, so we'll use it again. We're going to pretend that we started with 4 moles of our acetic acid. In this case, once again, we are adding our sodium hydroxide. So because we are not at the equivalence point, we do know that the moles of the sodium hydroxide should be less than what we are starting with. So again, I'm going to make up the number of 2, which keeps the numbers nice and simple. That's going to be a 0. Because we are before that equivalence point, our sodium hydroxide that we're adding is actually the limiting reagent, right? We have less moles of it than what we started with. So again, at this point, this is our limiting reagent. That's our excess reagent. That also means that the change we would expect at this point would be the moles of sodium hydroxide. That means when we are done, we will have 2 moles of this guy, nothing of that guy, couple moles of this guy. We can then convert this into molarity by using our total volume, obviously what we added in terms of sodium hydroxide and how much of the acetic acid that we are left with. Any questions on that ice table? So if you are not sure where to go from at this point, once again, we can use our ice table to help us. And if we do, we see we have this guy, which is sodium acetate left over, and we have acetic acid left over. These 2 guys, are they related to each other? They are. That is a weak acid and is conjugate base, also known as a buffer, which was your question. Yes. So how would I get to the pH of a buffer at this point? I could use an ice table, or I could use the Henderson-Hasselbalch. Yeah. So because it is a buffer at this point, we can use our molarities that we have of our weak acid and base. We could go in here. Obviously, the pKa here would be, in this example, based off of the Ka value of acetic acid, which would be like a 4.74 action if we actually did it. Alternatively, as somebody else mentioned as well, you could do an ice table as well. If you're going to do the ice table here, it would be the weak acid dissociating, if you chose to do so, into H+ and your acetate. And again, as we talked about a number of times up to this point, you want to make sure that you carry down both this molarity and also this guy here to start with. Otherwise, again, you won't be doing a buffer problem if you chose to do a second ice table at this point. You would just be doing the weak acid problem and you won't get the right answer. So if you chose the ice table, important to take down both of those guys to the proper spots. And obviously here you would solve for X, and that would be your H+ concentration into your pH, and it should give you the exact same answer as if you went into the Henderson-Hasselbalch equation, SpongeBob SquarePants equation, whichever one it may be along the way. So clearly here, as the titration starts and before the equivalence point, a lot more work there than what we got going on there in a strong acid, strong base titration. But once again, it is really just a buffer problem at this point, and you will always hit a buffer problem in this type of titration as you go from the first drop to before the equivalence point when you're titrating a weak acid and a strong base. This is also basically part 3 of the buffer lab, right? We just made a buffer from the reaction of a weak acid and a strong base. So this is what I was talking about earlier when we were doing that, and we're talking about that briefly, which is, in this case, the buffer itself is not made up of the sodium hydroxide, but we're using the sodium hydroxide to generate both parts of the buffer in this example. And that's what you want to do in part 3 of your lab, is basically use either the strong base and the strong acid separately. to generate the other part of the buffer in the right concentration that you ended up with the same buffer that you made in part 1 of the experiment. So this is what we were talking about earlier, that it is possible to generate a buffer from the reaction of a strong base and weak acid, or a strong acid and weak base. But again, the strong acid and strong base itself is not part of the buffer. As you can see in this ice table example, is completely gone at the end, right? So it's no longer there. And what you're left with is actually the buffer being generated. Any questions on that there? Tie that all together. Nice bow. All right. So a little bit different, a little bit more work in this titration. Who chose this one? All right. So let's talk about what happens at step number 3, which is our equivalence point. So at step number 3 in this titration, which is the equivalence point here, we're going to get a reaction still, I think, yeah, which is our acetic acid plus our sodium hydroxide in this example. And get you a little sodium acetate and some water. So because we're at the equivalence point, we're going to start with our initial moles here of acetic acid, which is what we're starting with. We are adding here, obviously, our sodium hydroxide to it. And because we're at the equivalence point, the number of moles of sodium hydroxide should be, in my example, 4, should be equal, right? Because they should be equal to each other. The moles of the acid should be equal to the moles of the base. So let's just take a moment here and think about this, which is a very common question that is asked to you, or a common way that titration problems are asked is they sometimes will not give you the volume to reach the equivalence point, but they will ask you to calculate the pH at the equivalence point. How could I figure out the volume to reach the equivalence point? Because you need that, right, to convert back to molarity, right, and all that good stuff. How would I be able to figure that out if it wasn't given to me? You could assume a couple of things. We could assume that you know the molarity of the base, right? And you know the molarity of the acid, and you know how much acid you're starting with. So let's assume those 3 things. No. So could I use molarity to figure out how much volume I would need? I could use the molarity of the sodium hydroxide, right? So first off, I know the molarity of this guy, which is moles per liter, right? And so I know this number, and I know that if I know nothing else, I know that at this point, the moles of the base I should have is equal. So I should know that number, right? So we could just very simply rearrange this and solve for liters, right? Which we convert to milliliters by just using the molarity of the sodium hydroxide. Yeah. You could also use a little dilution action, M1V1 equals M2V2, because this is a 1-to-1 relationship. You could actually use that equation. By the way, if it's not a 1-to-1 relationship, you should not use that equation because it assumes that the stoichiometry between the acid and the base is 1, by the way, which is why sometimes we look online, people say that's the titration equation, but only works really for a 1-to-1 relationship. And if you have anything other than that, it does not work really well. That is really the shortcut of doing a very quick stoichiometry problem of, let's just say that this was 0.1 molar, and I had 25 milliliters of it, and we'll just say this guy, well, we'll get there, it was 0.1 molar too. So if I knew the volume of my acid in this case, I could use the molarity of it, moles per liter of my acetic acid. I then could do the 1 mole of sodium hydroxide to 1 mole of acetic acid. And at that point, I will have my moles of sodium hydroxide, which then I can use my molarity here basically to figure out the volume. So this will do that calculation for you very quickly, and it'll be a shortcut, but should only be used for a 1-to-1 relationship between an acid and base. Otherwise, you'll have the wrong stoichiometry involved. All right, so those are a couple of ways that you can figure out, how much volume you need to reach the equivalence point if you don't know it, and sometimes they're not given to you. By the way, the other quick way as well is if it is a 1-to-1 relationship between the acid and the base, you will need the exact same volume of acid and base to get to the equivalence point. If they're exactly 1-to-1 and they have the same molarity, you'll need the exact same volume. So same molarity, 1-to-1 relationship, you need the same volume of each to get to the equivalence point. That's like the super quick way. All right. Any questions on any of those ways there? Back to my made up example here of 0 for that guy. At this point, since we are at the equivalence point, we can't pick the wrong number here. It should be the moles of everybody at this point. So we're going to do the moles of everybody. We're going to add some moles of this guy here. We're going to, as we would expect, zero out everybody on the left there. We're going to end up with 4 moles of this guy, which we can convert back to molarity. Once again, here at the equivalence point, we can look at our ice table and see that the only thing we have left over is our friend sodium acetate. That I believe is a salt. How do I get the pH, or what is the pH in this case? Is it 7? pH of this one is 7. So I feel like I didn't need to do the whole table if the pH was 7 at this point. It's a little bit, just a little bit higher. That's good. I like that. All right, it's like, it's not really 7. It might be just a tad bit higher than that. It's all right. All right, let's talk about this salt. This salt is basically 2 things. It is going to, as it's swimming around, having a good day, it's going to be sodium ions floating around, a little bit of acetate ions floating around in the solution. When we think about salts, we think about a certain type of reaction, which starts with an H, just called a hydrolysis reaction. Will sodium go through hydrolysis? Good answer. That is no. That is no, because that is basically came from a strong base. It's group 1, right? Will not go through hydrolysis. But our acetate here will. It will, because it comes from a weak acid, right? So very different than the strong acid, strong base titration, where we end up with a salt that is a neutral salt. Here we actually end up with a salt that decides, in addition to swimming, I'm going to go on and continue to react. So this guy will then go through hydrolysis, which means you get to do another ice table, because 1 is never enough here on the equivalence point. So we're going to have our acetate going to react with the water that's hanging out in there. And it's going to go through this hydrolysis reaction. Once again, we could use our logic to help us understand what's going to happen. It comes from a weak acid, which means the acetate should act as a base. And the definition of a base is it's going to accept the H+, right, from the water. The result of that is it's going to generate where it came from always, which is our acetic acid, and it is going to generate a little bit of hydroxide, which means now you will tell me it's going to be a little bit above 7 because it has some hydroxide that's here, which is basic. I said always minus 6 times in that sentence, and it's going to be basic because of that. That also means we're going to do an ice table where we're going to get our initial concentration from above. Yeah, so kind of the only purpose really of that first ice table is to get the concentration of the salt. So you can kind of do this. That's going to be done in molarity, which again is why it's good to convert back to molarity after that first table, because in this situation, you kind of need a molarity to get the right answer here probably. So make sure that you always kind of convert that back. This table is going to be a normal sort of table with zeros and X's in this case, right? And when we're all said and done, we'll have our initial minus X, our X, and our X. This would go into our K value here of our products over our reactants here. And by the way, this is a K, A, B, C, D, F, G. This is a B because we also see hydroxide here. The K values you probably have in this problem is the K, which means that's your KW, KA, KB conversion that you need to do. So you will probably have to do that. Also really important, when I finally do get to the point where I solve for X, X in this case equals, yeah, the hydroxide concentration, which means that's a POH first, right? And then a pH. So a little bit different than range 7 than we had in the last titration here. So what's going to happen in this type of titration, I think, what's going to happen in this type of titration between a weak acid and a strong base is you will always end up with a salt at the equivalence point, and that salt will always go through hydrolysis and it will always produce hydroxide. So we will always expect this type of titration to be basic when we get to the equivalence point. I'm going to tie it back into a knot here one more time. This is why we use phenolphthalein in the titration of acetic acid, which is vinegar, and sodium hydroxide, because that's a weak acid and a strong base like you did in Chem 50. That's why you chose that indicator, because it turns around a pH of 8.3-ish, which is around where that equivalence point would be if you calculated the actual equivalence point pH. So again, figuring out in this type of titration, you definitely would want some type of indicator that would change in a basic sort of range to choose to use to help you stop. If we were acidic at this point, that would again be a bad choice. Any questions on what's going on there? All right, so this titration a little bit different. So far, we've had a Ka problem. Yeah, we've had a buffer problem, and we've had the hydrolysis problem. The good news is those are all problems you've done before in this chapter. You just got to know when to do it, right? So that's the important part of it. So let's take a look at what happens as we are not deterred by that indicator changing color, and we continue on past the equivalence point in this case. So in this type of titration, once we go past the equivalence point, we again are going to have our same reaction. And now that we're past the equivalence point, we'll start with our same starting amount of acetic acid here, which will be our 4 moles. And since we are past the equivalence point, our sodium hydroxide should now be more than that, right? So just like the previous one, at this point, you're just dumping more base into your titration. So I'm going to make up the number of 6, which is more. So we're going to see really the same sort of effect that we saw in the previous one. We're going to see really a change in sort of what's the limiting reagent, what's the excess reagent. And in this case, it is the acid that's the limiting reagent. It is the base in this case that will be the excess. So we are going to take the smaller number here, and that's going to be our acid. That means at equilibrium here, we got 0, we got 2 moles, and we got 4 moles. Again, good practice at this point. We're going to use the total volume here to convert this back to molarity. And we're going to use our ice table to help us figure out where we should go in terms of figuring out the pH. So we got this guy and this guy. First question is it a buffer? It is not. So again, very common. People get to the end and go 2 numbers. Cool. I'm going to SpongeBob it there and get the Henderson-Hasselbalch equation going. And we're going to do that. But again, they're not a buffer here. So you cannot use the Henderson-Hasselbalch even if you have 2 values given to you at the end. We got our salt here, which we clearly just saw will go through hydrolysis, right? And sort of react. We also have this guy, which is a strong base. And as we saw earlier there a second ago, when this salt reacts, it's going to react as a base as well, right? So we basically are left with 2 bases at this point. Between the 2, which one is stronger? It is sodium hydroxide. So the acetate's got to go find some water, do a little reaction. It's an equilibrium type thing. It's going to generate a little bit of hydroxide. Sodium hydroxide just needs to go for a swim. Yes, as you turn it on and drop it into the beaker, that's all it needs to do to break apart, and it will generate hydroxide. So out of the 2, definitely sodium hydroxide is going to be the stronger base and really the major contributor to hydroxide in that solution at this point. So typically what we do at this point is we ignore the contribution of the salt at this point because it's pretty small compared to sodium hydroxide just going for a swim. And we look at really just the strong base. And that's good because at this point in this ice table, we pretty much have the hydroxide concentration given to us, which means we could then go into our POH and then into our pH at that point. So past the equivalence point here in this type of titration is actually similar to what happens in the previous one. except we will have a salt that will go through some hydrolysis, but in comparison to that strong base that you're just dumping in there, it's not going to be much of a comparison. That's going to be the major contributor. So we look at only the strong base contribution here at this point, which gives us our hydroxide contribution and our POH and our pH. Any questions on that one there? So the similarly looking curve here, that looks like the other one. A lot more happening here. So really a Ka problem there. You got a little buffer problem happening there. You got a hydrolysis problem there. And you got like a strong base problem happening at the back end of it. As I mentioned a second ago, the good news is, these are all calculations that we've done previously. The key where people really struggle is to recognize that they should be doing the proper calculation at the right point. This is why it's really important, as I've been going through these examples here, or these made up examples, talking about, are we before the equivalence point? Are we at the equivalence point? Are we after the equivalence point? It's sometimes easier, as they say, to do the calculation if you know what calculation you're supposed to be doing. So you literally should know in this type of titration what type of calculation you're doing, just based on where you are in the titration curve. And that makes doing the calculation a lot easier rather than jumping into the calculation and trying to figure it out as you go, which is what a lot of people do. And then they get U-turns, right? And go down wrong streets. Would you say, I don't need directions? I was there once. It's over there. I'm by that corner over there. We can take the left and then the right. And then you end up on the totally wrong freeway going the wrong way. And you never get anywhere. These are all analogies to an exam taking process where you get lost and you never finish your exam because you went on the wrong direction. So you want to think about, see what I'm doing there? I don't know what I'm doing, actually. I'm just making this up as I'm talking. So I never really took chemistry. It's okay. It's reassuring. But it's really important really to sort of figure those things out, because like I said, you really should know the type of calculation, you should know how it ends up. You could even get really specific, like that at the very beginning here, you need one ice table with molarity. And the second step, you need one ice table to get the concentration of the buffer. And then you could either go another ice table as your option, or in the Henderson-Hasselbalch, at the equivalence point here, you need minimum of 2 ice tables, one to get the concentration of the salt, one to do a hydrolysis problem. So these are things you want to think about, what you need to get yourself to the end and where you are so that you can get yourself to the end of that. Any questions on any parts of that? Well, let's do one, shall we? Why not? Now let's have some fun here. Let's do, let's go with, let's say we did a titration here of, we'll use our 25 milliliters of 0.1 molar acetic acid. And we want to know, what is the pH after we add, let's do 22.5 milliliters of 0.1 molar sodium hydroxide. And let us go with a Ka value of 1.8 times 10 to the minus 5 for acetic acid. All right, give it a go. See what you come up with. I'll do it as well. Okay, let's take a look, see how we're doing. So again, this is pretty much like the titration we've been talking about. So in this case, we have our sodium hydroxide up in the burette. We are adding it to our acetic acid down in the beaker or flask in this case. So we are going to get obviously our reaction here of our acetic acid plus our sodium hydroxide. And again, double displacement, which is going to give us something here. Sodium acetate looks good. And a little bit of some water here. Once again, since we are doing our titration and we're starting with this guy and we are adding this guy, we do need to convert to moles. So for our acetic acid, we got to convert our milliliters into liters. So 0.0250 liters. Timesing it by the molarity of our acetic acid, which is 0.1 moles per liter. Going to give us that same sort of starting number there that we had before, I think 0.00250 moles. We'll do the same thing there for our sodium hydroxide. We got 0.0225 liters times our 0.1 moles per liter, and 0.0225 times 0.1 going to give us 0.00225 moles of sodium hydroxide. So those are going to be our initials here. So 0.00225 moles, 0.00225 moles, and 0. Am I before, after, or at the equivalence point? Before. I am before. Once again, what I am starting with is more moles than what I'm adding, or vice versa. What I'm adding is less moles than what I'm starting with. So we are definitely before the equivalence point. Before the equivalence point there. We'll just use a bunch of abbreviations there before the equivalence point. So we will then use the sodium hydroxide as our limiting reagent in this case. So we're going to go minus 0.00225 minus 0.00225 and plus 0.00225 moles. That is going to get us 0.0, too many zeros, 2 5s minus 0.002. I know, as if I did scientific notation, I wouldn't have it all. But now I'm going to write more zeros for you. So 0.000250. There you go. Another 0 there in case we don't have enough. And 0.00225 moles. I'm going to now add my total volume at this point to convert back to molarity, which is good practice here. So we started with 25 milliliters of our acid. We added 22.5 milliliters of our base to it. That's like a 47.5, I hope, milliliters. We're going to convert that to liters. So we want to divide it by 1,000 or move our decimal place so that we can convert this properly back into molarity. So that's going to give us 0.00025 divided by 0.0475, 0.00526, and 0.00225 divided by 0.0475, 0.047. I'll call it 4. Why not? Any questions on that there so far? All right, at this point, again, we can look at our table here, and we got this guy left over, sodium acetate and acetic acid, and that should tell us it is a buffer, which we should have already known before we started, right? Because we were before the equivalence point in this type of titration, which means we should always hit a buffer at this point. So we should always basically hit that buffer. At this point, you do have the two options. I'm going to go with the Henderson-Hasselbalch equation here. So our pH is going to be our pKa plus the log of the base over the acid. Our pKa value going to come from the Ka value for our weak acid, which is 1.8 times 10 to the minus 5, and it gives us a 4.74. That gets us a pH is equal to 4.74 plus the log. Which one's my base? Sodium acetate, as the acetic acid would be my acid, right? So that's going to be 0.0474, 0.00526. Hope for the best here. 0.00526, a little log action, a little 474 action, a little 569 pH as our pH. Question on any part of that? Once again, at the end there, you could have done a second ice table using acetic acid, again, with an initial molarity of the acetic acid and an initial molarity of the acetate on the other side of the arrow in that particular case. You see how we did. We were at 22.5, which is like in this ballpark. So we were between those two numbers. So that's pretty good. Probably didn't screw up. It's reassuring. I know, probably didn't screw up there. Any questions on weak acids, strong base titrations? Yes. All right, one last look at our titration curve here, which is somewhere. It coming, maybe. There it is. Looks upside down to me. And this is going to be a titration of a strong acid with a weak base, like a little NH3, which is a weak base, and some hydrochloric acid, which is a strong acid. And dare I say, you get a little ammonium chloride. Or if you like to keep it separated, NH4 plus and Cl minus, whichever way you like. In this titration, it is a little different. Up in the burette is actually the HCl. Down in the beaker there is our NH3. We are actually adding acid to the base in this titration. That is why my titration curve looks upside down, because I am starting at the basic area because I have a base, and I'm adding acid, which means my pH is starting to drop. So it's kind of the same curve, just starting high and going low. The other two, we started low pH and ended high because we're adding base to it. Same four parts to this titration curve before we begin the titration, before we get to the equivalence point, at the equivalence point, and past the equivalence point would actually be down in this area here. So let's start tearing this one apart here at step number 1 before we start the titration. The only thing we got sitting there in our beaker or flask is a NH3 in this case, which is a weak base. Yeah. How do I find the pH of a weak base? How do I find the pH of a weak acid? I should do an ice table. I was going to go through my whole story again about being at the thirst oasis and doing the crushed ice. We would do an ice table because it is a weak base. If you can't have fun, you know, you really shouldn't do anything. So because it's a weak base, obviously we would have a KB value given to us. And in this particular example here, we would do an ice table based off of our ammonia, not ammonium, but ammonia, plus a little bit of water. And again, it's going to accept the H plus. Gonna make a little NH4 plus in this case, and hydroxide. I'm gonna separate them. You could keep them together, but we can clearly see the hydroxide in this case, which means obviously we will be using our KB. This would be an ice table with molarity at this point. Again, we haven't added any volume, so we have no problem. So we could just use the initial concentration of our weak base. The rest of the ice table is pretty much the same there. We're going to have our initial minus X, our X, and our X as I write through every picture on the page there. In this case, though, we will solve for X. And as we can see from our ice table, X in this case is actually, once again, the hydroxide concentration. So again, not the H plus concentration. So that's going to equal the hydroxide concentration, which means we could go to our POH first and then to our pH. So this type of titration is a little bit different than the last one, but kind of similar, except that we are starting in this case with a weak base versus a weak acid. Still going to require the same ice table, sort of, but a KB type of problem. So KB problem like we did at the beginning of the chapter, just like we did KA problems. You would do a KB problem here, solve for X, that gets you your hydroxide concentration and gets you your X value. And then you get your POH and into your pH. At this point, we would then roll into part 2 here, but we will stop.